Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on December 22, 2025, just yesterday. This paper proposes unified autoencoding, a frequency-factored tokenizer that unifies semantic abstraction and pixel fidelity in one latent space, and it boosts ImageNet reconstruction PSNR from 18.05 to 29.65. The paper is titled The Prism Hypothesis, Harmonizing Semantic and Pixel Representations via Unified Autoencoding. Alright, as we go, the Prism idea about low and high frequency features ends up being a pretty clean way to understand why this works. Also, the authors shared an official UAE GitHub repo, and it mainly gives you the codebase plus a quick evaluation script to reproduce the reported metrics. You will find the unified AE module, utility and model helper files, and example commands with config and checkpoint paths for running ImageNet and Coco evaluation. Figure 1 explains the core claim, which is that meaning and detail live on a shared frequency spectrum. The full diagram lays out the prism metaphor, where frequency means coarse, global patterns at low frequency, and sharp textures at a high frequency, kind of like separating a photo into smooth shapes versus edges. The left side lists natural inputs like images and text, and the right side maps encoders onto low and high frequency bands, motivating UAE as the unifying latent. Figure 2 makes the Prism hypothesis concrete by showing where different encoders spend their representational energy across frequency bands, where low frequency means broad shapes and semantics, and high frequency means edges and textures. The full plot summarizes normalized energy versus frequency band K. The left side at band 0 shows Dyno V2 and clip peaking strongly, which matches a semantic focus. The green SDV curve stays higher into mid and high bands, so it preserves more fine detail. Figure 3 shows how unified autoencoding keeps meaning and detail together by splitting features into frequency bands and supervising them differently. This full diagram lays out the whole pipeline, from the input image through both encoders and into the pixel decoder. The semantic-wise loss aligns only the low-frequency bands, because those bands carry cross-modal meaning. The pixel-wise reconstruction loss then pushes the higher frequency bands to recover texture and sharp edges, so the output stays faithful. Table 1 shows that splitting the latent into low-frequency semantics plus high-frequency detail translates into much stronger reconstructions. The full table compares methods on ImageNet 1K and MS Coco, using PSNR and SSIM for fidelity, and RFID for perceptual realism, where lower is better. The UAE Dyno V2 base row jumps to about 30 PSNR on ImageNet. The UAE Dyno V2 large row reaches about 33 PSNR, which is the strongest fidelity in the list. Table 2 shows that the unified latent is not just good for reconstruction, because it can also drive class conditional generation. The table reports standard generative metrics, where generative FR Eckert inception distance is a realism score and lower is better. UAE reaches about 1.7 on generative FR Eckert inception distance, which stays competitive with strong baselines. The inception score is also high, which suggests decent sample diversity alongside realism. Okay, 2 takeaways stand out. Semantic alignment mostly lives in low-frequency features, while pixel-level realism needs those extra mid and high-frequency bands, and unified autoencoding makes that split explicit, so one latent can serve both jobs. The broader implication is that frequency is a clean knob for unifying tokenizers across tasks like retrieval, reconstruction, and generation. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.